Is by Kevin Buzzard, and he will speak on potential modularity of residual representation.
Does residual representation just mean row bars, as it were?
It's up to you.
I think it must mean mod L representations. So instead of preparing a talk, I just spent the last 10 minutes thinking about analogies or some rubbish. So here's some stupid. Here's a picture of the mathematical world, and then there's a very steep hill. And here are some statements about, statements of the form rho is modular. And here are general statements. So this is just something I had in mind when I was just trying to not understand the details of what was going on, but somehow the general situation. So we have this. So this theorem of Deligne and others, Eichler and Shimura and Deligne, given pi some kind of holomorphic Hilbert modular, holomorphic automorphic representation for GL2. Of the Adels of F, whatever you want to call it, a Hilbert modular form, if you like, then there exists some rho, blah blah, some rho gal F bar over F to GL2 of QL bar, attached to pi, right? Attached to pi.
This is F totally real?
Yeah, F totally real.
But even though it's not Deligne.
No, it's lots of people. Deligne et al. It's mostly Carriol, I guess, tonight. And but it's something that Tobias mentioned already. So now we know what rho bar. Now we know what it means to be. But you see, what I want to stress is that somehow this theorem is easy because we were allowed to start with a modular gadget. We were given pi, and once we've got pi, we've kind of made it up the hill, as it were. Once we've got something modular, we're up the hill. So given a pi, we want to construct a rho, and then the kind of hope is that given a rho, we want to, given a rho plus some conditions, we want to deduce that rho is modular, right? That's somehow where we're going, because by the end of the fourth talk, we should have, given an elliptic curve, rho would then be its Tate module, or maybe the dual of its Tate module. And we want to find some modular form, possibly after changing the base. But this is clearly harder because this is going uphill, right? This is going uphill. If we start off with something, if we don't have a modular form in our given data, then we want to get a modular form, it's the harder part of the direction. A Deligne statement is, given the modular form, we get the representation, but given the representation, we want to get the form. And historically, we know it's harder because this was done in the 70s over Q and maybe in the 80s for a general totally real field, in the early 80s. But it took a lot longer before Wiles came along and kind of. So how do we get up the hill?
Sorry, I can't avoid remarking. Don Blasius has been emphasizing a lot in this lecture, going down a steep hill.
Yeah, maybe. Well, here I'm gonna freeform. So I'm trying to emphasize. So you see, these theorems of Ribbit, right? These theorems of Ribbit, things like level lowering, say things like rho bar modular of level n implies that rho bar is modular, of some other level of level m, where m is typically either n times p or n divided by p. But again, these should be. Again, you're up the hill, right? Because we've deduced that rho is modular, but we started. We had some modular form pi 1, and we've ended up with some modular form pi 2. But we didn't have to climb the hill because we had the modular form already, and we massaged it. And even even these modularity lifting theorems that Fred was talking about, these are the form rho bar modular plus some assumptions. It implies rho modular. And there's a huge amount of effort that's gone into proving this kind of thing. So the first one is Taylor Wilds, and now we have much more streamlines. But still, we didn't go up the hill. Right? We still started at the top because we were given some modular form that was right mod P, and we've right mod L, and then we've massaged it until we got a modular form that was right. So these are all, these all live at the top of the hill, right? All at the top. So how do you get up the hill? How do you prove a mathematical theorem that starts with some statement that doesn't involve modular forms and ends up with a statement, ends up with some conclusion that something's come from a modular form? So I guess maybe there's some theorem of maybe Hecker. I'm not so sure. Hecker and maybe something like Hecker and Weil. I'm not sure. I'll write down a statement. Let's say L over K is a quadratic extension of number fields, and we have some chi from gal L bar over L to, let's say, C star, just a continuous character, with chi doesn't equal its conjugate. So gal L bar over L has an outer automorphism, as it were, or the abelianization of gal L bar over L has an outer automorphism coming from an element of gal K bar over K that isn't in gal L bar over L. So let me call that C. So if chi doesn't equal its conjugate, and if rho is the induction, if rho is the ind from gal L bar over L up to gal K bar over K of chi, so that's now a two-dimensional representation, and this assumption means it's irreducible, is the irreducible two-dimensional representation induced by chi. Then rho is modular, right? In the sense that it comes from an automorphic representation of GL2 of the adels of K. So rho is associated to some pi on GL2 of the adels of K. So what I'm trying to stress is that this is of a very different nature, this result, because I didn't have modularity as an input, and I've got modularity as an output. So that's gone up the hill. And there's other clues that it's of a very different nature to these results over here. I didn't assume that rho was odd, and I didn't assume that K was a totally real field. So the machinery you used to do it wasn't algebraic geometry. The proof of this is analysis, right? In some sense. Sorry?
You can get this from the converse theorem?
Here's a very easy proof. So the proof is that L of rho comma S equals L of chi comma S. So that's how induction works. And this is an L function with lots of good properties because it's a one-dimensional L function, right? This has analytic continuation plus functional equation, as do all the twists.
Where is chi not equal to pi?
Oh, I wanted rho to be irreducible. If rho is reducible, then I have to tell you what an Eisenstein series is, and there's somehow more than one definition in there. So this L, because this is like a Dirichlet L function, or some analog of a Dirichlet L function. This has analytic continuation and functional equation, as was proved by Hecker in the 30s. And Tobias mentioned that given a modular, if you have pi, a Hilbert modular form, then that implies that L of pi comma S has analytic continuation plus functional equation. He mentioned that. But it turns out that there's some kind of converse to this. If you have some two-dimensional representation such that the L function has analytic continuation functional equation, and so do all the twists of the L function, some huge amount of data. So if L of rho comma S has analytic continuation plus functional equation, plus the L function of all the twists of rho, if they all have lots and lots of functionally nice properties, then that implies that rho is modular. So there's an example. There's one way of getting up the hill, and it's really the first. It's the first. This is an uphill theorem, right? So for let me call that kind of representation dihedral, because it's somehow So if we can kind of get up here with kind of dihedral representation. That's one way of getting us up the hill, is if you're in a situation where representation's dihedral. And really, in some sense, there's very few. I need a rubber. Oh, there's one. There's very few other ways of getting up this hill.
Well, you could say that chi is already up the hill.
Chi is up the hill, because for GL1, maybe this is the GL2 world. And for GL1, it's not a hill, right? For GL1, it's a walk. For GL1, it's only class field theory getting up the hill for GL1.
No, very unfair to him.
Yeah, okay.
Much more than class. He didn't even have class.
No, not in its modern form.
No, not even in its Artin hadn't proved it. But
He hadn't got the Artin.
It's analytic configuration in 1910 or something like that, 1912.
Is that right?
Yeah. Look at his collected work.
Okay, and Artin wasn't until that's 1930.
1927.
Okay. So you see, what Fred was doing was mucking around up here, potential modularity theories. But I've got to get up the hill, right? So here's one more example of getting up the hill. Is Langland's tunnel theorem, right? So again, the proof of this involved some complex analysis. So Langland's tunnel is this theorem if rho from gal, again, K, I'll just have a general number field K to GL2 of C has solvable image, and is irreducible if you like. Has solvable image, then rho is modular. Then rho again is isomorphic to rho of pi for some pi on GL2 of the Adels of K. And again, this is clearly not proved using algebraic geometry, because again, K doesn't have to be totally real. K can be an arbitrary number field. Rho doesn't have to be odd. Pi doesn't have to be holomorphic. And again, so the proof of this is lots of hard analysis. You need non-Galois cubic base change, for example, and to do the A4 to the S4 case. So these are proofs of very different nature, but they're going up the hill, so kind of solvable. I should say also really that the assumption is not that rho is solvable. The assumption is that the projective image of rho in PGL2 of C is either dihedral A4 or S4. And it's just a coincidence that those happen to be precisely the solvable subgroups of PGL2C.
So you seem to regard analysis as the hill.
Yeah, yeah, you see where I'm coming from. So now how did Wiles? So Wiles proved that semi-stable elliptic curves were modular, right? So the point of this digression is the following. So it's a theorem of Wiles and Taylor-Wiles. If I also include Fred, then I can. And it's easier to state it. If E over Q is semi-stable, I'm trying to give a history. I know that stronger theorems have been proved now, but I'm trying to kind of give some kind of historical. Because this is again the 70s. If E over Q is semi-stable, maybe early 80s, then E is modular.
That's already Wiles.
They did semi-stability? I thought they had semi-stability at 3 and 5. Okay, yeah, you're right. I'll remove you. Semi-stable at 3 and... I wanted to write the shortest possible statement. You were semi-stable at 3 and 5, only that was the point. That's what you did once, I think. So there's a theorem. It's and so this has got up the hill somehow, because we start off with an elliptic curve, which is definitely not a modular gadget a priori, and it's become modular by the end. So the question is, how do they get up the hill? So at some point in the proof, they've got up the hill. And the way they do it is they piggyback on Langland's tunnel. So here's the proof. You piggyback on Langland's tunnel. up the hill. So here's the proof is, the formal proof is step 1, prove a modularity lifting theorem. So rho bar modular implies rho modular. Okay. And now, so of course here rho is going to be the dual of the Tate module, and rho bar is going to be the dual of the p torsion for some p. So secondly, you apply to E of 3 Q bar, because GL2 of F3 is coincidentally a solvable group. So you're very lucky. So apply to E of 3, so I mean, strictly speaking, the dual of this and the Tate module, the three-adic Tate module of E. Right, that's your rho bar, and that's your rho. You see, rho bar, if rho bar is irreducible, it's modular by Langland's tunnel, because as GL2 of F3, not only is it solvable, as I say, solvable isn't good enough, is not only solvable, and it has a two-dimensional representation, has a faithful two-dimensional representation, fortunately. So we've got a representation to GL2 of the field with 3 elements. We can lift it to a representation to GL2 of C. We apply a load of hard analysis. When did I start, by the way? I have no clue. 1/4, I assume. And when do I stop? Is it 1/4 again, or is there some 10-minute thing? So we got up the hill using Langland's tunnel. Unfortunately, this proof isn't finished yet, because if you look at the assumptions that Fred had here, the kind of assumptions where one of them was that the first one was rho bar restricted to something was absolutely irreducible. But the problem with working, I mean, if Wells was working with, with the prime 691 or something, he would have been in good shape. But GL2 of F691 isn't solvable, so he has to work with this small number 3, and elliptic curves can have points of order 3, so kind of warning, what if E has a point of order 3? You see, Wiles didn't know how to do this case for a long time. I think he could prove if E had no subgroup of order 3, I think he could prove it was modular a long time before he announced modularity proof in general in this room, right? So if E's got a point of order 3, or more generally a subgroup of order 3, then the first assumption that was there in every single one of Fred's theorems that he stated, then we see then rho bar equals E of 3 is reducible. So we haven't really got up the hill somehow. We want an irreducible modular thing before we can kind of get going. So Wiles introduced the 3-5 trick, which is the point of all this waffle. Wiles introduced the 3-5 trick. So let me tell you the 3-5 trick. Because that's the heart of this talk is going to be a big generalization of the 3-5 trick. So here's the 3-5 trick. Say E is some elliptic curve over Q, and kind of E of 3 is reducible as a Galois representation of Gal Q bar over Q. How are we going to prove that E is modular? Let's try to find another elliptic curve. Let me call it A, such that A3 is irreducible. So again, this is an elliptic curve of a Q. So now we're going to be able to use modularity lifting theorems to prove that A is modular, and that A5 is isomorphic to E5. There, as gal q bar over q modules. So now the funny thing is, that's enough. That's enough to prove that E is modular. Why is that? So let me say it's semi-stable, if you like. Let me say historically what happened. So, whilst we're trying to prove all semi-stable elliptic curves are modular. So here's the funny thing. So if A exists, E is modular. So why? So let me carefully go through the argument. Here's the argument. I assumed that the 3 torsion was reducible. For firstly, and that implies that the 5 torsion is irreducible. Why is that? Because if the 3 torsion were reducible and the 5 torsion were reducible, this elliptic curve would have a subgroup. So because E5 reducible implies that E has a subgroup contains C of order 15. That implies that E gives me a point on x0 of 15 defined over Q. Unfortunately, this has genus 1. And it's got genus 1 and such a low conductor, so it must have rank 0. And you check it does have rank 0, and there's only 4 non-cuspidal points, and all of those correspond to elliptic curves that aren't semi-stable. You can just do an explicit calculation. So x0, 15 is the compactification of the modular curve y0, 15. And y0, 15 is the moduli space for elliptic curves with a subgroup of order 15. And the Q rational points on things like this correspond to elliptic curves over Q with a subgroup of order 15 defined over Q. It's not quite right. You have to be a little bit careful because of twisting. But that's basically, what I've written is basically true. So there's a funny trick. What's so funny is we're essentially relying on the fact that all these numbers are small, right? So E5 is irreducible, and hence, so for E5 is irreducible, so now here's the argument then. So we've got A3, so let's try and let's make it semi-stable as well. So now here's the idea. So we've got A3 irreducible implies A3 modular. That's going up the hill, right? But that's Langland's tunnel. So there's the hard work. It implies that A is modular by modularity lifting theorems. This is one of the things that Tobias mentioned. So that implies that the 5 torsion is modular. And that implies that the 5 torsion of E is modular. And that implies, again, by modularity lifting theorems, that E is modular. So we're left with one issue, how to find this A. So let me just mention how that goes. So we've used the fact that x0, 15 had genus 1. I mean, if it had genus 0, it would be sunk. We'd have to use another prime. But we were lucky, x0, 15 had genus 1. There's this whole catalogue of small dimensional coincidences that got Wiles' proof to work. I mean, as well as all the hard machinery, he was somehow, in some sense, quite lucky that he could see his way through. And this A, so the construction of A, here's the idea. There's a module, I mean, you consider the moduli space, so construction of A, you consider the moduli space parameterizing elliptic curves B such that the 5 torsion in B is isomorphic to the 5 torsion in E. So that's some smooth projective curve, some It's a smooth affine curve. If I furthermore demand that the Weil pairings match up as well, some technical, it's going to be a smooth geometrically connected affine curve. And E, the elliptic curve E itself, clearly its 5 torsion is isomorphic to itself. E gives a Q point on this curve. And again, now you do a calculation, and again a miracle happens that the genus is 0. So we've got a curve of genus 0 with a rational point. It's a smooth curve of genus 0 with a rational point, so it's got infinitely many rational points. There's a huge number of rational points, but they won't all do, because some of them will correspond to, it's actually a little bit too, we don't need A to be semi-stable everywhere, I should say. We just need to be, not any rational point will do. For example, we need the 3 torsion on A to be irreducible, and the 3 torsion on E is reducible. But you can check that somehow the points on here corresponding to elliptic curves with reducible 3 torsion are kind of quite a slim subspace. So there are problematic points which won't correspond to A, but so you can check that the problematic points are small in number, and so hence A exists. So that's, Wiles uses something called the Hilbert irreducibility theorem to do this. But if you're prepared to use a sledgehammer, then what you could do is you could consider the cover of this moduli space consisting of elliptic curves whose 5 torsion was what we want and whose 3 torsion had a subgroup of order 3. And that would be a degree 4 cover of this genus 0 curve. And you compute the genus of that, and it turns out to be genus 3. And so by Falting's theorem, the problematic points are actually finite in number. But if you don't really want to use Falting's theorem, then you can, as I say, you can use something called Hilbert irreducibility. Hilbert irreducibility. So that's the 3-5 trick. And the 3-5, so Wiles has lots of ideas in his paper, and ideas get generalized as time goes on. So what happens to the 3-5 trick? So the 3-5 trick was used by several people to prove several other. So let me just give other examples of where the 3-5 trick was used.
An elementary question. Did you say in the case where the 3 torsion is irreducible, there is no gap in the first group? Is that what you said earlier?
That's not, no. That was before he found the gap.
Yeah, but
The gap is.
it's something else.
Yeah. So he had a false proof, but he thought he had a proof.
Right, but you said something about that he knew how to do something long before something else.
Well, he didn't know how to.
Before.
Right.
He didn't want to announce that he could prove that semi-stable elliptic curves with no subgroup of order 3 were modular, because then he felt people would leap. He knew full well that the moment semi-stable elliptic curves were modular, you had the prize.
Right.
The prize being Fermat
Right.
at the time, when it was considered hard. So he didn't want to let on, and he spent a long time trying to prove an R equals T theorem for E3 when the thing was reducible. And that's why papers like Skinner-Wiles appeared, because it had so many ideas about reducible deformation theory. That's why Skinner-Wiles exists, basically, because it had all these ideas trying to fix this. And then he found this silly 3-5 switch, and he found that in May, and by June he was standing in this room explaining the proof. The moment he found it, he realized it was done.
The fact that it has genus 0, it only works for 5 or something?
Yeah, x of 7's got genus, where's Gianta? What's the genus of x of 7? There you go. Yes. So what happened to the 3-5 trick? I wrote down some other examples of some. I wrote some other historical examples somewhere. Oh, maybe I didn't. I'm looking for the word Nick Shepherd-Barron. He was mentioned as well. Oh, here we go. I thought I did. So the 3-5 trick was generalized to other small numbers. So an example of what I gave is a theorem of Nick Shepherd-Barron and Taylor. This is Nick Shepherd-Barron and Richard Taylor. Is that if rho bar from gal q bar over q to GL2 of the field with 5 elements is irreducible, and det rho bar equals the cyclotomic character, well, the inverse of the cyclotomic character because of our normalizations, then rho bar is modular. So the proof of that's not the 3-5 trick. The proof of that is find an elliptic curve whose 5 torsion is rho bar. So that was one of the things they proved. And the second thing they proved was if rho bar goes from gal q bar over q to GL2 of the field with 4 elements is unramified. I think they had unramified at 3 and 5. That implies that rho bar is modular. So how do you prove part 2? To do part 2, so as I say, the proof of this is, part 1 is find an elliptic curve, find E over Q, such that E of 5 is rho bar. And then part 2, we've got a mod 4 representation. We use a 4-5, use a 4-5 trick. There. So what's a 4-5 trick? Well, the problem is I can't find an elliptic. I mean, if rho bar is surjective, that's the hard case. If rho bar isn't surjective, the image is solvable. But GL2F4, the Jordan-Holder factors of GL2F4 contain A5, the alternating group on 5 elements, which is simple. So it's slightly too big. It's slightly too big for Langland's tunnel to carry up the hill. But you see these tricks somehow. You see, they're getting a little bit better now. We're kind of getting up with A5 somehow. some A5 representations there, because we're using the 4-5 trick. So here's the proof of 2, is that you simply write down an abelian, consider the moduli space of polarized abelian surfaces. I mean, I won't go into the details. Abelian surfaces with an action of the integers in Q root 5. There's Z1 plus root 5 over 2. So the idea is that this moduli space, plus, I need some more, plus some, plus a full level, plus a full level 2 structure. Well, plus an isomorphism from polarized abelian surfaces A, plus an isomorphism with the 2 torsion of A, isomorphic to rho bar. See, rho bar is a representation to GL2F4, but 2 is inert in this field. So this has an action of F4. So instead of being a 4-dimensional representation of the field with characteristic 2, it's actually a 2-dimensional representation of the field with characteristic 4. So that moduli space, again, because the numbers are very small, this is geometrically a tractable gadget. This is some other point. It's not, I don't think it is rational. And this is why Nick was used somehow. You now have to find, we want to find a rational point, right? So you use some, hard, sort of tricky geometry. Tricky geometry implies that this moduli space has a Q point, has lots of Q points. There. So you choose you make a carefully, so you find a Q point corresponding to some abelian variety A, such that the 5 torsion, or the root 5 torsion, right? Because 5 is ramified in Q, is irreducible. You see, by some kind of, this space has got enough Q points. The argument is much more delicate, and I can't say I've ever read it, because it was just somehow, I didn't know enough geometry. So now the idea here, so now you know what the proof is. Now we've got the root 5 torsion is irreducible, so by modularity lifting theorems, So now you see, here's the proof. So now, a root 5 modular, because we've got these there by part 1. Remember, part 1 was proved by Langland's tunnel, right? Langland's tunnel got us up by looking at 3. Part 1 we've assumed, we've had to use 5, and now so a of root 5 is modular implies a modular implies a of 2 modular. And that's the end of the proof. So that's the 3-4 trick. And then Gianta did something, right? Gianta then 6 isn't prime. Gianta didn't fall into that trap. He considered mod 7 representations. Actually, maybe Schecker considered mod 6 representations, I think, at some point. Because you can still, give the problem then is you've got a representation to GL2F2 and a representation to GL2F3, and you want to prove they're both modular coming from the same modular form. You can ask that question. So maybe Gianta and Ahamian did something. He proved that certain representations rho bar from gal Q over Q to GL2 of F7 were modular, plus conditions implies modular. And again, the idea is you looked at the moduli space. So it's got genus 3. You couldn't necessarily find a Q point, is that right? But you found some point over a solvable extension.
Yeah, I just got a very simple equation.
So it wasn't just genus 3, but somehow it was you had a projective embedding of small degree. Yeah. So you historically the first person to write down a non. So you found not a Q point. So we're going to look at elliptic curves, right? We're going to look at elliptic curves whose 7 torsion. So let's consider the moduli space of E such that E of 7 is isomorphic to rho bar. That's a moduli space of elliptic curves, but it has genus 3. So it may have no points over, right? Maybe no Q points at all. So Gianta's observation was to find an F point. Is that right? For F a totally real thing. Whose observation? But it's not just a random curve of genus 3. It's a curve of genus 3 for which equations have been known to Gauss or something. I just said somebody. But there do exist points defined over totally real fields of small degree. So we see now, so you don't actually prove that rho bar is modular, you prove that rho bar restricted to some subgroup of finite index. So the moment you find an elliptic curve defined over F, we now, so now let's just, now you use some machinery at 3 to prove that elliptic curve over F is modular, and then you deduce that rho bar is modular not as a representation of gal Q bar over Q, but as a representation of, so that implies that rho bar restricted to gal F bar over F is modular. And because F has got sufficiently small degree, you can use base change to get back again, I guess. Is that the idea? Yeah. So it implies that rho bar is modular.
You mean F is solvable? Or?
Sorry?
You mean F is solvable?
Yeah, you see F has got degree, this is like some degree 4. This is some degree 4 equation. So there's some point defined over some number field of degree 4, and its Galois closure it doesn't have degree less, it has degree less than 60. So it must be solvable.
And so for these F points that you find, you also examine the 3 torsion? Is that what you're saying?
Yeah, you find an F point that's good enough for the curve to be provably modular. So there's a kind of a history. This is, in my mind, I mean, it only occurred to me when I was kind of doing a history, this is a crucial. Everyone else was finding points over Q, and Gianta's found a point over a field that isn't Q. So you see, we're kind of we've slowly got more. Do you see, you're never going to prove Sayre's conjecture this way. If you just leave the universe as it is, eventually people will be proving representations of GL2F23. No one had any ideas, but just kind of kept tweaking things. You're going to run out of steam at some point, because all your curves are going to have genus 19. and you're somehow going to be doomed. So this is somehow never going to prove anything. But now Taylor, what Taylor did, sorry?
For Platonist, we should mention Ellenberg also.
Well, because he did F8 maybe?
F9.
9. So Jordan Ellenberg. You're absolutely right, thanks. He did representations to GL2 of F9. And it's the same trick, right? He uses a Hilbert modular surface. But yeah. So,
same trick as the Schiffer-Curran and so on.
yeah, as everyone. You're going to realize you're going to write down a moduli space of abelian varieties such that your P torsion is what you want it to, your L torsion is what you want it to be, and then you're going to use an argument on the P torsion for some P not L to prove that the thing is modular.
But some of these cases where you end up with surfaces, I guess you were saying they're quite different from the first case. Like
Well, it's harder work, only because I don't know. I say that because I don't know anything about the geometry of surfaces. Peter's here. I was be careful what I say. I went to a course by him from geometry of surfaces.
But roughly,
But it's all right. He's not listening.
I mean, do they produce curves on the surface of some sort?
Huh?
You produce curves on the surface of some sort?
I can't tell you what these people do. What Schiffer Baron Taylor does. So let me give my talk. So that's the background. So here we go. So chapter 1 now. So section 1. Taylor's theorem. So here's a theorem of Richard Taylor from 2001. I'm not going to write down what he writes in the paper, because when I was trying to read it, I found I couldn't understand the proof. Let's put it that way. But I'll write down something simpler for which I do understand the proof. So if L is bigger than 2, and K is a finite K is a finite field of characteristic L. If F is totally real, if rho bar goes from gal F bar over F to GL2 of K, so note, very different to what I've been saying for the last 20 minutes. I've been talking about fields of very, very small cardinality, one-digit cardinality. So this theorem, I'm trying to suggest it's similar to this sort of thing, but there's a huge difference here, is that K could have a million, billion, trillion elements. Well, that's not prime. If rho bar looks like that, and if I make some assumptions, and if det rho bar are better be the inverse of the cyclotomic character. I should say that I've made slips all the way through. Every time I said that the P torsion elliptic curve is modular, I meant that its dual was modular. I think our definition of modular will have determinant equal to the inverse of the cyclotomic character. So that I've missed out some duals. But so the emphasis is still. Plus some local conditions, and if I'm going to do this, I'm going to say rho bar restricted to GV looks like cyclotomic inverse times psi v 0, 0 psi v inverse for all v dividing L. So there's conditions at L. I mean, clearly I'm not going to say then rho bar is modular, because that would be a dream. It certainly would have been a dream in 2001 anyway. So here's Taylor's observation. Then there exists some f primed over f, a finite Galois extension, Did I say it was odd? I said its determinant was epsilon inverse, so that implies it's odd. Then there exists f primed over f, a finite Galois totally real extension, in which all primes above L split completely. Such that rho bar restricted to GF primed is modular. So there. Now where does that sit?
Psi v is not a ramified character?
No, doesn't have to be.
It's any
Yeah, so it's psi v anything. Any k star valued character. But yeah. So where does that sit? This is one of the reasons that my advisor is a genius, right? He's somehow realised that he doesn't. There's a funny. This is a potential modularity. This is, as far as I know. As I said, I hinted that Jayanta proved a potential modularity statement, but then he deduced a modularity statement. Taylor is making no attempt to get back down from f primed back down to f. He's not trying to prove that rho bar is modular, but he has started with nothing and he's come out with a modularity statement, so he's kind of he's somewhere up the hill, right? So here's Taylor's result. Taylor's result. It's somewhere halfway up the hill. It's somewhere up the hill because he has some.
You're not saying that it's solvable, essentially.
No, if he could prove it was solvable, he could get down again. If he could prove it was solvable, he would win, and that's why Jayanta won, because his f primed had small degree, and so you could use sort of known base change results to get you back down.
What does Taylor state in his paper? Different from what
Taylor has a star here, and I can't see how to control Taylor. I can't see how to control that star.
he admitted that you can't see?
Well, we've had a lot of dialogue about various issues of this paper. Remarks. Remarks that 1, f primed is not known to be solvable over f. If you could get f prime solvable over f, you could prove lots of things. You could probably prove Sayre's conjecture, probably prove the BDJ conjecture, I'd imagine. And so it probably isn't solvable over f. And in fact, if you look at the explicit construction of f primed, it will have absolutely enormous degree. Only a potential modularity result. So, how far up the hill is it really? Somehow it's not going up there. He's going a different way. Taylor's forging his own path by formulating a potential modularity result. But it has incredibly strong applications, which is why he proved it. Well, which is why he wrote it down.
You could just strike out this condition if you didn't insist that the times above L split complete.
Yes, because then I could change f. Yeah.
So when you say there's a completely different road here, are you saying it doesn't use this analytic result?
I'll tell you the proof. I've only got 10 minutes left. I'm going to tell you the proof anyway. So are you going to mention applications, Jayanta? Because what you get from this, maybe I'll just sort of say something without writing it down. The kind of corollaries this theorem has are if you have rho, a p-adic and l-adic Galois representation, such that rho bar is irreducible, then you can prove that rho is potentially modular. So because rho bar is potentially modular, then you apply your modularity lifting theorems over f prime, not f. And so you get so the kind of corollaries you get, if you have rho just from gal f bar over f to GL2 of O, which is geometric there, plus some local conditions, plus rho bar irreducible, f z2 of O. So implies that rho is potentially modular, and that implies that things like the trace of rho of frob v is in Q bar, for example. That's absolutely non-obvious, and that implies that, so it implies that implies that the L function is well defined, somehow independent of your choice of isomorphism of Q bar with, well, there's only so it implies things like this. And it also implies that the L function of rho comma S has a meromorphic continuation plus functional equation. I mean, that wasn't known at all, right? Take an elliptic curve over a totally real field. I don't think the elliptic curve was known, the L function was known to have meromorphic continuation before this. So this, because you see the idea is that potentially modular, but then somehow it's modular over this totally real field, and then you just simply induce back up to F. This is somehow an idea. You get all sorts of things. So this potential modularity is a lot nearer the top than you might think. That's what I'm saying. Because it has powerful, I mean, if you knew that rho was modular, you'd know this thing had analytic continuation and functional equation. But meromorphic continuation and functional equation, I mean, this kind of thing was enough for Sarto-Tate, things like this, you see. So these are really eye-opening results, you see, because what Taylor's observation is that potentially modular isn't quite what we want, but it's good enough for many of the consequences, for example. So that's the amazing thing. So here's the proof. You just do a PL trick, right? So what do we want to do? So first, we've got some rho bar. We want to prove that rho bar is. Let's try and prove that rho bar is modular, and we'll get stuck. And when we get stuck, we'll relax our ideas and try and disprove potential. Let's try and prove rho bar is modular. So we want to use. Let's use the PL trick, as it were. That's the whole point of this talk, is I've been trying to explain that there's this funny 3-5 trick. So here's how the PL trick is going to work. Let's write down a random dihedral, absolutely irreducible representation sigma from gal F bar over F to GL2. Rho is a mod L, rho bar is a mod L representation, right? So I'm going to go to GL2 of, I want a finite field of characteristic P. If I put kappa, can people distinguish my kappas from my Ks? Let's go with that, unless someone shouts. If they shout, they have to shout out a better piece of notation. So kappa is finite of characteristic P, not equal to L. So sigma has nothing, sigma bar, of course, because it's a mod. Sigma bar has nothing to do with rho bar. The source of sigma bar and rho bar are the same Galois group. But the targets are 2x2 matrices over fields of different characteristics. And rho bar is an arbitrary representation, and sigma bar is a dihedral representation. It's just induced from some quadratic extension. So this is a kappa. So F is going to be totally real. Let me induce it from a totally imaginary quadratic extension. So now sigma bar is known to be modular, right? So sigma bar is modular by Hecker, by dihedral. That's the answer to your question. That's all I'm going to use. That's all the analysis I need. So I'm removing the Langland's tunnel. So sigma bar is modular by Hecker. No real analysis. So great, I've got a modular representation sigma bar is of the wrong characteristic. It's nothing to do with the representation you're interested in. But that's going to imply that rho bar. I'm still amazed by this. So now let's consider the moduli space of. So let me choose a nice big coefficient ring, a coefficient. Choose a curve. Choose a big number field. Number field M, such that OM has primes contains some primes p and lambda, right? Such that OM modulo p going to be isomorphic to kappa, and OM modulo lambda isomorphic to k. Those are our two finite fields. So now we consider the moduli space. Oh, M had better be totally real. Consider the moduli space of Hilbert, of polarized. Let me not get into the details, because one won't make mistakes if one gets to of polarized abelian varieties. Well, of polarized abelian varieties of dimension M over Q. So you see, this is an analog of this, elliptic curves with a point of order 5, but these are possibly huge dimensional. So abelian varieties A plus fixed isomorphisms that preserve. I mean, I need to pick a pairing. I better have det of sigma bar is cyclotomic in there. I'm going to choose some plus isomorphisms. AP isomorphic to, which one is the P torsion? That's sigma dual, and AL, A lambda, isomorphic to rho bar dual. And these isomorphisms have to preserve some. I mean, everything is self-dual. These are self-dual coming from the Weil pairing on the abelian variety, and these I just fix. I just choose a random isomorphism of the thing with its dual. And I can do that because the determinants are all cycloinverse. And these isomorphisms have to preserve that symplectic pairing. So now in the old days, this was a curve of genus 0, or an abelian surface. In the old days, when P and L were small, this was a curve of which we had some kind of, you had some means of handling it, right? We had some means of handling it. So ideally, let me give that note. Let me give you an X. So ideally, we'd like an F point on X. So this is where Taylor's proof then differs from everything else. Before I used to say, but X has got genus 0 and it's got 1 point on it. Or, but X is a surface which is geometrically very easy to understand. But you see, we don't. X is some incredibly complicated high-dimensional variety about which we can say very little. So no, this is not possible. But we can find an R point on X. I should maybe say this is a moduli space. This is over F algebras, right? Because this is an isomorphism of gal F bar over F modules.
How does one know that it is non-empty at all?
Oh, the moduli, the complex points are just, this is no condition now. Because this is representations of gal C bar over C. So over the complexes, this is just a Hilbert modular variety of full level PL. So you know it's uniformized by copies of the upper half plane. So it's geometrically connected and irreducible and smooth. So ideally we'd like an F, so this is no good because we've got a random algebraic variety, how can we find a point on it? But we can find R points. We can find R points on X because building abelian varieties over the reals isn't that difficult. You build, again, Swinders and Dart taught me how to do this as well. You build complex abelian varieties by looking at C to the G modulo lambda. And to make sure the abelian varieties are defined, and then with some condition, you need to have some positionally holomorphic functions. But if lambda is somehow coming from, if lambda looks a bit like OM squared, then you'll have these. But you want, that's no good. That's an abelian variety of the complexes. You want it over the reals, but you just make lambda equal to its complex conjugate, as it were. So lambda equals, lambda carefully chosen equals lambda bar, carefully chosen. And then the conditions here are just says, because there's no abelian varieties, this is always the representation of the group of order 2, which is 1 and -1, as it were. So you can find R points on this thing here. And a theorem of Morey-Bailly,
Are points you mean any embedding?
any embedding you like, because all the complex conjugations are behaving the same. Yes, for any embedding f into R. So furthermore, so a theorem of Morey-Bailly there exists some totally real field f primed such that x has f prime points. You see what we've done here? We've moved from the local situation to the global situation. I've checked there's no local obstruction at infinity. I've only checked it at 1 prime. So this is not a number. This is an algebra. This is arithmetic geometry, right? So x over f, smooth, quasi-projective, geometrically connected variety. There. So if the theorem is if x of r is non-empty for all embeddings of f into r, then there exists some totally real field. You see, this isn't a local to global principle, because I haven't said there's an f point, but I can find a number field which is totally real. There. And in fact, even better. So you see, we're done, right? That's the proof, nearly. So hence, result follows. Except, I've lost the result, haven't I? Except f primed may not be totally split at v for v dividing L, and that's kind of a pain, because when you wanted to prove modular, you don't want to make your f prime to be too big, because you'll somehow lose control. Maybe I should remark that the first thing I thought when I saw this was maybe f prime is so big that it kind of contains the kernel of rho bar, and then rho bar restricted to f prime, just the trivial representation, and you're not really proving anything. But maybe I should remark that if rho bar, if the image of rho bar is not solvable, if the image of rho bar is solvable, we're done already. But if the image of rho bar is not solvable, then it implies that rho bar restricted to gf primed is irreducible for all totally real f primed. There, because you know that rho bar is odd, you see. So we're still getting an interesting representation. So that's the proof of Taylor's theorem, apart from the fact that f prime isn't totally split at v. So Morey-Bailly didn't really prove this. Morey-Bailly proved an analogue of this, but actually for a finite set of places. So how are we going to fix this? So to get f prime totally split at L, you see f prime is totally split at infinity. To get f prime totally split at L, we need, well, at v dividing L, we need an fv point, right, for all v dividing L on X, you see. And then Morey-Bailly says the idea is if you find fv point, what he actually proved is that if you have fv points for all v dividing, if you have fv points, then furthermore you can assume that f prime is totally split at v. That's the idea. So it's an analogous thing. If you've got r points, then you can assume f prime is totally split at infinity. If you've got fv points, you can prove it's totally split at v. So now the final piece of work he has to do, which is some of the technical heart of the paper, is to construct an abelian variety over a local field. So we need a HBAB over FV, giving a point on the moduli space. So however, you see, I use complex analysis to find my abelian variety over the reals, whereas this is much harder work because somehow the analogue of c to the g modulo lambda is the take curve and generalizations of that, and they only give you representations with multiplicative reduction. And if rho bar, it was epsilon inverse chi 0, 0 chi inverse. If chi squared isn't the identity, then you're never going to get an abelian variety with multiplicative reduction. So you need to construct an abelian variety with good reduction for which the P torsion and the L torsion are right. So how do you do this? You use Honda-Tate theory. Gives you an abelian variety over QV, I think it was called, over FQV. So the finite field, the residue field of this, and then you use Sayre-Tate. Careful application of Sayre-Tate lifting gives you an abelian variety over FV on the moduli space. So the insight is that if he wants a global point on his moduli space that satisfies certain local conditions, he can use his theorem of Moret-Bailly and just check the local conditions are non-empty. So that's how he proved his theorem. But in fact, all of this is no longer necessary, which is good because it's the hardest part of the paper. No longer necessary. Because now we have better modularity lifting theorems. I kind of insisted that F prime was totally split at all primes above L, and that was to keep control. And now, because Kissin's much better at modularity lifting theorems than anyone else was, we don't need so much control. So the analog of the construction is at this point, we have our moduli space X, we want to find an F primed point with certain local conditions which are rather weak. And we try to find an FV point, but if there isn't an FV point, then we simply make a Galois extension of FV until we find a point. And then we say, well, there's bound to be a point somewhere, and so we just find some point over some finite Galois extension of FV, and then you feed that back in, and your corresponding theorem, I won't write down, what the modified theorem is, but there'll be weaker conclusions about F primed. You can't conclude it's totally split at L. You can only conclude things like it's unramified at L or something like that. But those are good enough for what Gianta needs. So there you go, that's how it works.
Any questions? Comments?
It's easy.
So just to, I guess you already said this, but just to make sure I heard correctly. So these two local conditions, totally real and totally split above V, all has to do with their application to modularity or lifting theorem, right?
Yes, that's why you want them. Yes. But the theorem of Moret-Bailly, that I never stated properly, is that you have X over F quasi-projective connected. And if you have X of FV non-empty for all V in some finite S, some finite set of places, implies there exists some F over F primed over F totally split at all V in S, such that X of F primed isn't empty. That's what you're after. And in fact, you can make it to risky dense, I think. So yeah, at the time, Taylor had much weaker modularity lifting theorems, so he had to really make sure that he hadn't lost control of his extension at L, for example. And so he had to work hard. He had to put all the primes above L into S. Whereas nowadays, the only thing that goes into S is all the primes above infinity. Because you can be much more free about what's going on in the other places.
But you're storing some condition on the A at primes over P?
Oh, I should say, to do this, there's something I should have said. To get all this to work, you need 23 tedious extra conditions on sigma bar and P. Right? There's all sorts of conditions.
No, but
What did you ask me?
so even using the stronger modularity lifting theorems, so you're going from sigma bar being modular to...
I should say that sigma bar is not only modular, it's modular when you restrict to an arbitrary totally real field. That's
right.
okay, but it's because it's induced. Right.
So you want to go from sigma bar, restricted or whatever, being modular, to the p-adic Tate module of A
Absolutely.
being modular.
This is a 3-5
So you
trick.
still need some hypothesis on the A at primes over P, the residue characteristic of...
I don't know what you mean by A at the prime of P. P.
Well, you need to know that A is
Oh, your F primed
ordinary
point.
or
Yes.
according-
Yes. So he also has to find.
No, even with the stronger modularity lifting.
Right. So what he's going to do is he's going to choose a prime P. He's going to choose a prime P such that rho bar is unramified at P and rho frobenius at P has got two distinct eigenvalues. And then he's going to choose this sigma bar. So yeah, it looks ordinary at P. Does that answer your question? So sigma bar looks ordinary at P, and then he's going to make sure that F prime is totally split at all primes above P as well.
Okay, and then
He's going to have to do all this as well. So I've suppressed this.
sorry,
He being Richard, to prove that he wants, he also needs an HBAV over F curly P.
I'm asking what one still needs.
What one still?
What you still using stronger modularity lifting theorems, using Kisin for example.
Yes.
You still need something. You can't just take an arbitrary point.
Yeah. What do you need?
You would need something like A to be.
Yeah, your F prime is going to be unramified at P, for example. Will that do?
F prime will be unramified at P.
And I'm going to choose sigma bar. F is going to be, P is a completely auxiliary piece of data, right? P is going to be 100 digits. It's going to be, everything's going to be unramified at P. F will be unramified at P, rho bar will be unramified at P. Sigma is going to be carefully chosen so that it looks ordinary at P. F primed is going to split completely at P. Are you now happy? Because now my local condition, I've got an unramified. F primed is now unramified at P, or all primes above P. The representation looks ordinary.
So then you don't even need Kisin's theorem.
I don't need Kissin's theorem to prove what Taylor says, but I think Jayanta wants to immediately deduce from what I've just said that rho is potentially modular if rho bar is. So I don't need Kissin's theorem to prove this. You're right, but I need Kissin's theorem to prove the obvious corollary. Because L could be ramified. So the next line is when you need Kissin. Jayanta needs it. Yes, but on the way we don't need Kissin. There you go.
And we meet again, let's say in 5 minutes.
What?
Supposed to be in a while.